Welcome. I'm Moshe Wasserblat from Intel Labs. I will take the next 25 minutes to present future text classification for the medical domain. I start by introducing myself. In my former role, I led the NLP research group at NICE Systems. We were the first company to deploy speech recognition, emotion detection, and text analytics solutions in call centers, including healthcare. I'm currently leading applied NLP research at Intel Labs. We are very active in NLP research, and our goal is to explore features that disrupt hardware architectures and increase adoption of deep learning in the industry. The NLP healthcare market includes solutions that automatically extract, generate useful knowledge from large textual data. For example, structuring the information in medical reports into patient charts, or recognizing in advance that someone is at risk. The last 3 years were exciting for NLP. It seems very like every week we have a new breakthrough. Started in 2018 with transformer architecture, then BERT based on transformer that outperforms human in many NLP tasks. In 2020, OpenAI released GPT, a model that can generate high-quality medical data and recently advances genetic and biology by improving the ability to predict how DNA sequence influences gene expression. However, adoption in the industry is low. Survey by O'Reilly show that the lack of high-quality data is the main bottleneck holding back further adoption of AI technologies. This is also communicated by IBM CEO. He stated that data challenges are halting AI projects, and recently, Andrew Ng launched a data-centric campaign for shifting the focus to the quality of data. In this presentation, I'm going to focus on document classification in medical domain and demonstrate methods that can moderate the data scarcity and data quality bottlenecks. Text classification or doc classification is the process of understanding the meaning of the unstructured text and organize it into a predefined classes. According to recent survey by Gradient Flow that mapped the NLP use cases in production system, 48% of large companies use NLP for document classification. Doc classification in healthcare has been deployed to extract valuable insight from medical reports, scientific papers, and free text. Here is one example. An adverse drug event, ADE, is defined as harm experienced by a patient as a result of exposure to a medication. A significant amount of information about drug-related safety issues, such as adverse effect, are published in medical case reports that usually can only be explored by human readers due to their unstructured nature. AD have a severe impact. In inpatient setting, ADs account for an estimated 1 in 3 of all hospital adverse events, affect about 2 million hospital stays each year. In outpatient setting, ADs account for an estimated 1 million emergency department visits and approximately 125,000 hospital admissions. The ability to automate the detection of AD-related phrases in unstructured text using AI models can help preventing ADs for safer and higher quality health care services, reduce healthcare costs, and inform and engage consumers. Another example is classification of open questions related to COVID-19. In this specific data set, the goal was to label each question into 15 different categories and over 200 subcategories in order to provide high-quality service, prioritize response, and support top public concerns. Few-shot learning is a promising research direction for text classification. On the left circle, we have standard training. It requires high amounts of labeled examples per task, usually hundreds or thousands. On the middle circle, we have few short learning. In this setup, we usually have only a few labeled samples. A typical few short scenarios include between 50 to 200 samples. And on the right circle, zero shot learning. It is the holy grail where no labeled data is needed for training at all. Few shot learning is the most typical scenario in production because labeling of data is time-consuming and costly, and commercial environments are very dynamic and contain domain shift between test and training data and always need continuous training and fine-tuning. The main question in real-world environment is how to classify docs in low-resource setting where a very small amount of labeled data is available. I will first present zero-shot learning and then continue with data augmentation, a method for automatically generate training data, synthesize new data. So let's start with zero-shot learning. Hugging Face transformers, this is kind of famous library for NLP, includes several models for zero-shot learning. In just a few lines of code, you are able to build a zero-shot pipeline where you only have to set your class names, and the model returns a similarity score for each class for new query input. This is what we can see here in the slide. Another option for zero-shot learning is to simply download a pre-trained language model that was already fine-tuned for your task. In most cases, such models are trained using general available data like tweet or social feeds, but not too much medical data. This may cause the model to output unexpected results. The example here shows a sentiment analysis model that was fine-tuned on tweets and generate poor results for medical data. The model predicts that tested negative for COVID-19 has a negative polarity, which is not true, of course, for medical domain. In general, zero-shot models are still under exploration, and their out-of-the-box accuracy is not sufficient, although they can be used to set as a minimum performance bar for other methods. Data augmentation is a common method to handle data scarcity, using diverse techniques to synthesize new samples or augment the training data. There are many data augmentation methods. Let's focus on the three most common ones. The first method is based on replacing keywords such as nouns, hopefully not changing the meaning of the sentence. The replacement is based on thesaurus or word embedding distances. The second method is back translation, for example, translating an English sentence into French and then back from French to English to generating a sentence with similar semantics but different phrasing. And the last method is based on generative models. Using a fine-tuned language model, such as BARD GPT-2, new samples can be generated by using the class label and a few initial words as the prompt for the model. Libraries like NLP.org and TextAttack provide very simple APIs for applying the above NLP data augmentation techniques. The framework is agnostic and can be easily integrated into your pipeline. Now let's examine the performance of data augmentation. To simplify, we demonstrate on a very popular text classification task, sentiment analysis of tweets, which aims to categorize unstructured text by sentiment polarity, positive or negative. The table shows the classification performance of different models when only 50 or 10 examples are selected per class as the training set. Sadly, data augmentation doesn't work well. It improved performance only in some cases, as you can see here on the 10 sample example, and the improvement not very significant. And in some other cases, it even adds the accuracy, as we can see here for the 50 examples case. So the question is, what else can we do? Now we will present two very strong methods for low resource setting. The first, you probably heard about GPT-3. GPT-3 was designed to work in low resource scenarios. And second, I will present a new method called sentence transformer fine-tuning, or in short, SetFit. Transformer model sizes are growing exponentially, starting from birth in 2018 with over 300 million parameters, continuing with GPT-3, 170 billion parameters, up to NVIDIA Megatron with 500 billion parameters. These large models open the door for exciting and creative application, ranging from website design based on texture or vocal instruction to music or art generation. As an example, this image shows an automatic design generation of a chair in the form of avocado based on text description only. Now the question is how we can utilize those large models for learning to classify documents in low resource settings. When GPT-3 paper came out, the paper headline was "Language Models Are Few Shot Learners." Indeed, GPT-3 excelled in such low data resource scenarios. As we can see on the right-hand side, on Superglue, a popular benchmark for text classification, GPT-3 score improves as model size increases. For 0-shot, 1-shot, and few-shot, 32 samples scenarios. How does GPT-3 work for text classification? The mechanism is called in-context fine-tuning. This is what we can see here in the image. In context learning, models directly generate the answers based on input to output training examples provided as prompt without changing their parameters. GPT-3 utilized in-context learning to demonstrate superior few-shot capabilities in many NLP tasks, including, of course, text classification. GPT-3 major disadvantages are that it required the model to be huge, 175 billion. It relies only on the pre-trained knowledge, which is problematic if it was trained before COVID-19 and we want to extract classification on such data. In addition, it requires extensive prompt engineering and provides only limited prompt length. In the following slide, I present SetFit, which is a simple and efficient alternative for few-shot text classification and few performance results for few-shot setting on different data sets. Let's start with Draft. Draft is a data set for real-world text classification benchmark, which allows only 50 samples for training. It includes 11 practical real-world tasks, such as medical case report analysis and 8 speech detection. The benchmark includes results produced by GPT-3 that became a standard baseline for comparisons, specifically for few-shot scenarios. We conducted a POC for SetFit, which I explain in a moment, using a model that is 1,600 times smaller than GPT-3. To our surprise, our very efficient model significantly outperformed GPT-3. Our model's results came in first place after the human baseline, And these results are quite encouraging since they show that it's possible to produce very efficient models that compete and even outperform the large model like GPT-3. So now let's look under the hood of SetFit algorithm. The best way to explain SetFit is visualizing the ID first introduced by a similar challenge in image classification. In a classic deep learning / machine learning scenarios, like in this image, this is of course a simple example. The goal of an image recognition system is to detect and identify football images. The model, in this case a CNN, needs to be trained with thousands of images of football and thousands of images of backgrounds. In such way, the model learns salient features that represent the football category and uses them to classify new images as football or other. The drawback of this method is that it doesn't work well when given small amount of lab data, of course, a few shots an hour. The network is not capable to effectively learn features and detect patterns that represent the category. In 2015, Koch presented a one-shot method for image classification. One-shot means that we basically have only one example per class, which is, of course, a few shots in a setting. The idea is very simple and inspired from human learning. Humans are very good in capturing similarity acquired by years of evolution. The fact that we were able to recognize a wild animal that we probably didn't encounter in the past give us survival advantage. So how this mechanism works? So first, on the left side, the network is trained with many pairs of similar and non-similar objects. The network is becoming quite good in encoding features that help recognize similar object and non-similar object. Now at the right side, at test time, only one example is given per class. The network encodes the examples and calculates a similarity score between the test and each class. The test will be categorized to the class that received the highest score. In this example, this is the basketball category. And this is a kind of the formal deep learning explanation. The architecture is based on a bi-encoder network, and the goal is to minimize a contrastive loss function. The network is trained to maximize the contrast between images of different classes while minimizing the distance between images of similar classes. On convergence, that network learns to represent image embedding in a vector space such that similar images are close to each other and distinct images are far from each other, as we can see on the right-hand side of the slide. Now let's go back to our text classification tags. So on the left side, we have the bi-encoder network for sentences. Here the CNN model is replaced with BERT. From architecture perspective, it's looked at the following way. We input a pair of docs, sentences. Each doc is passed individually through the BERT network. The output of the BERT network is pulled using min pooling, resulting in a fixed size vector. And the two vectors representing the two docs can be compared using cosine similarity that reflects the semantic similarity between docs 1 and docs 2. On the right-hand side, we demonstrate the pre-training step. Large amount of pairs, even in the size of billions, is used to pre-train the bi-encoder network with similar and non-similar sentences. Then the doc, a new doc, can be encoded by the network to output their embedding representation. This is what we see on the picture below. You actually don't need to train those models yourself. The pre-trained model can be downloaded from sbird.net that includes Sentence Transformer Library, which is a model hub for sentence transformer representation, including abstract API and code examples for training and fine-tuning such models. So the flat system includes the following step, and I will demonstrate for two class. The first step is download a pre-trained sentence transformer. You can download such models from SBIRD. The second step is to fine-tune it on your in-domain data and generate it randomly from your training set. This is based on the low resource training set that you have. And finally, the third step is to train logistic regression in order to find a hyperplan that separates between the classes. And at the SetFit in inference phase, the SetFit model is used to predict the class, of course. It mostly resembles the training phase. In the first step, we use the fine-tune sentence transformer in inference mode to generate an embedding vector for the unlabeled inference instance as the input, as we can see here in the image. Then we use the trained logistic regression to classify the embedding vector to one of the two classes. For example, if it's sentiment analysis, it's positive or negative classes. So now let's look on some results. So we go back to our sentiment analysis example with data augmentation. I added the result of SetFit and GPT-3 versus the data augmentation methods. You can see that both GPT-3 and SetFit are significantly better than data augmentation. And SetFit is even slightly better than GPT-3, even with lower number of training sample per class. And regarding the ADE dataset example, label doc as positive if include adverse drug effect. Here are the results of SetFit and GPT-3 versus other popular models like AdaBoost, GPT-2, and BART in zero-shot model. This is what we see here in the table. The training only allows 50 labeled samples in total. In this case, humans substantially outperform GPT-3 on ADE, but this is quite obvious since it requires medical expertise. What we see here that SetFit outperform GPT-3 and significantly boost performance versus the other model. And last, the zero-shot model that we discussed at the start of the presentation has the lower performance. Here are the results for the COVID-19 question classification data set. We allowed only 20 samples per class, typical few-shot scenario. In total, 15 questions categories. The results for BERT plus data augmentation, as reported in the paper, is 58.1. And what we see here that SetFit outperformed the best result with significant gain and even get to close to 75% accuracy. Of course, this is only with 20 samples per class. Okay, and to summarize, these are the main takeaways from this session. So I presented kind of a quick overview of SetFit. This is a simple and easy method for few-shot learning. As we saw, it adopted similar contrastive learning, often used for image similarity. I also showed that the task-specific optimization outperformed generic cloud model like GPT-3. Again, a very simple interactive code example can be found in this link. And also, the link to the blog is given below in this slide. Soon, we will be able to have more details and model that will be available through Hugging Face and SBIRD. And thanks for listening, and let me know if you try SetFit yourself on your own data. Thank you very much.